So happy Monday to everyone. And today we're going to resume our regular material by looking at change of basis. And we're going to see, why we have been considering all sorts of other bases other than the standard one. So let's write down our objectives. So let me remind you that let's start with a linear map from R2 to R2. Okay, so let's suppose that so let's say that this is your linear map. Then the question that I'm going to pose is, what is the matrix of T? With respect to the basis, to the standard basis. Okay, so what is the matrix of T? What you're supposed to do is take the vectors of the standard basis, always computing the matrix with respect to the standard basis is pretty much the most straightforward thing. So you can take the vectors of the standard basis and compute their image. So you will get 2, 1. And you need to express that image as a linear combination of the vectors of the standard basis. So this will be 2 times 1, 0, plus 1 times 1, 0, 0, 1. And that will be the first column that you're going to put in that matrix. So you will have 2, 1. And then you're going to do the same thing with the second vector. And you're going to get negative 1, 1. And this is going to be negative 1 times 1, 0, plus 1 times 0, 1. And you're going to put negative 1, 1, right? And of course, if you were supposed to do this with respect to another basis, so same map. So how about the basis 1, 1 and 0, negative 1. The first thing that I would like you to notice is that whenever we ask for the matrix with respect to such a basis, we make sure that we give the vectors of that basis in an ordered fashion, meaning we specify which one is the first, which one is the second, which is achieved by putting them in the brackets like this. And so I'm going to compute T of 1, 1, which is going to be 1, 2. And I would like to express this as x times 1, 1 plus y times 0, negative 1. If you solve this system, you can easily find that x is equal to 1 and y is equal to negative 1. So this means that you will have the matrix 1, negative 1. And if you compute T of 0, negative 1, practically we did that in the previous when we found the previous matrix. So you will get 1 comma negative 1. And this will be, again, I can put x equal x times 1, 1 plus y times 0, negative 1. And then I will have to solve it. X will end up being, again, 1, and y should be equal to negative 2. So you will get 1, negative 2. And that 1 comma actually gets 2, not negative 2. And that will be your matrix. So you see, the matrix depends on what basis you choose. Okay, so that's one first thing, one first conclusion that we can draw. And the important thing that we can say here, the important remark that we can make here, is that it really depends on the, we really want to find the simplest possible form for a matrix. So one of the fundamental questions in linear algebra is, given a linear map, how can you find a basis for the underlying vector space, assuming that the linear map has domain of definition and target space the same one, so that the matrix of that linear map with respect to that basis is the simplest one. Today, we're not going to explore the question of how we find the simplest possible basis. We're going to explore the question of how we transition from one basis to another. So we're going to learn about the transition matrix. The general idea here could be posed as follows. If somebody gives you coordinates of a vector with respect to one basis, how do you find the coordinates with respect to another basis? That could simply be a description of what we're trying to do today. Okay, and there is a very simple method to do that. So imagine, so suppose that we have two bases, U and V, in Rn. Let's say that we're working in Rn. What I'm saying could have been true for any other vector space, but let's say that we work in Rn. So how can we find the coordinates of a vector in terms of the basis V, if we know its coordinates with respect to the basis U. So that's the okay. So basis, I'm using basis as the plural of basis. So so in other words, basis, I'm taking this to be the singular, and basis, that's the plural. Okay, thank you for asking this. Unfortunately, words that come from foreign languages sometimes give us this kind of strange plurals that we're supposed to get. But yeah. That's what happens. Now, the idea is the following. To transition from a basis U to the standard basis, we just need the standard basis, let's call it E. We just need the matrix whose columns are the coordinates of the vectors of U with respect to the standard basis. So in other words, let's give an example. So let's say that we have U to be 1, 2, 1, 0. And if we have V to be 1, -1, and 0, 1. So what I'm saying is, if I take the matrix U that has as its columns the coordinates of the vectors in the basis U, which is 1, 2, and 1, 0. So you can see how I constructed this. I just took the coordinates of these vectors and I set them as columns, right? So if I do that, then basically what I'm saying is that this transitions us from U to the standard basis. By the same token, the matrix V, which is, now I'm going to put the coordinates of 1, -1, 0, 1. This transitions from V to the standard basis, which means that its inverse will give us the transition from the standard basis to E, to V. Okay, so now if you put the two things together, you can surmise that the transition matrix from U to V is V to the -1 times U. So that's our formula. This is our main formula for today. The transition matrix is going to be V to the -1 times U. And so that means that all you need to do is compute the inverse of V. Okay, do we remember how to find the inverse of a 2x2 matrix? It's the only matrix for which we gave a certain general formula. So we said we take yes, you can do it that way, or you can simply take 1/2 times 1, 1, and then this will be 1 and 0. So the general formula, I remind you, is that the inverse of A, B, C, D is 1 over AD minus BC times D here A here, negative B, and negative C. Shouldn't it be -1? Yes, you're absolutely right. So no. Not -1, sorry. This is fine the way it is. So that's one. Okay. That's it. Okay, so now you could take b to the -1 times u. Can you explain why it's not -1? Of course. In our formula, it says that we have -c here, right? -c. Because remember, we multiply with the whatever sign is implied for the corresponding position. So since we had -1 here, the opposite of -1 is 1, okay? So that's why, according to this formula, yeah, you're right. I don't know why I put 1/2. Thank you. Yeah, the determinant is 1. Thank you for catching this. Yeah, so it has a very, very simple inverse matrix. Thank you. So if you want to find b to the -1 times u, then that is going to be 1, 0, 1, 1 times 1, 2, 1, 0. And this will give you 1 here, 1 here, 3 here, and 1 here. And that's your transition matrix. Okay. Questions, please. Let's do an example. The bottom row is 3, 1. So 1, 1 on the top and 3, 1 on the bottom. Okay, let's do an example. So find the transition matrix from the bases 1, 1, 1, -1 to the bases 1, 2, 0, 1. It should be easy for everybody to see that the vectors that I gave you here are linearly independent and in each of the two cases, okay? And also, I would like to give you a second question, which is if the coordinates of a vector with respect to the first basis are 1 and 3, what are the coordinates of the same vector with respect to the second basis? Okay, I'll give you a couple of minutes to think about these two questions, then we'll do them together. Okay, so let's try to explain everything in detail here. So let's call this basis U. Okay, U bar, V bar, and this is V bar, right? Which means that the matrix U that gives you the transition from the basis U to the standard basis will be 1, 1, 1, negative 1. Sorry about this, some technical difficulties. And the matrix V that gives you the transition from V to the standard basis is 1 to 0, 1. What we want to find, of course, is V to the negative 1 times U, right? That's what we wish to find. What is V to the negative 1? V to the negative 1, according to our formula, is going to be the determinant is again 1. That's very nice. Then you have 1 and 1. And then it will be negative 2 and 0, right? If you notice, actually, V is an elementary matrix, so it's only natural that this is going to be the determinant. So when you multiply these two matrices, you get what? You get 1, 0, negative 2, 1 times 1, 1, 1, negative 1. And this is the same thing as 1, 1, negative 1, and negative 3. Okay, so that's your transition matrix. So now, what does it mean that you have a vector whose coordinates are 1 and 3? What this means is, if I call this vector u1 and this vector u2, I'm looking at the vector 1 times u1 plus 3 times u2. That's what it means to say that the coordinates of a vector are 1 and 3. That means that the coefficients that you need to put in front of u1 and u2 in order to get your vector are the numbers 1 and 3. And you can ask now, how should we express same vector using v1 and v2, where v1 is this vector and v2 is this vector? And what I want you to do is that's exactly the kind of information that the transition matrix gives you. So I take my transition matrix, I multiply it by the coordinates of the vector with respect to the basis u, and what I'm going to get, one second, there is a question, shouldn't the 0 and the negative 2 be switched? No, again, let me, okay, okay, good. So if you go back to the formula, you will realize that they are the same. They are, you have negative C instead of C and negative B instead of B. So what you're going to get is 4 and negative 10. Okay? So we're going to get 4 and negative 10, which exactly means that the same vector, if you want to express it using v1 and v2, is going to be 4v1 plus negative 10 v2. That's what is going on here. Okay. So you can take the coordinates of a vector with respect to one basis and transform them into the coordinates of one vector with respect to the same vector with respect to the other basis. No, unfortunately, you couldn't have done that. V times u to the negative 1 is not the same thing as v to the negative 1 times u. Okay, it doesn't work that way. And the reason for that is you cannot just indiscriminately change the neither the order in which you multiply those matrices. So you couldn't even say u times v to the negative 1. And certainly you cannot move the negative 1 from one matrix to the other. I'm not sure that this statement is entirely so. I would say, technically speaking, I explained what these matrices are, so let me repeat it. So this matrix actually gives you the transition from U to the standard base C. This gives you the transition from V to the standard basis E. And this gives you the transition from E to the standard basis V. So now do you see how when you multiply these two matrices together, you first transition through this one from from U to E, and then you multiply with this one and that transitions you from E to V. And so altogether, the product creates a transition from U to V. Okay, that's the idea behind this formula. And there is something else, of course. I mean, this whole process involves finding inverses of matrices. And we know that one of the standard methods that we have used in order to find inverses is the Gauss elimination method. So here comes the question. Is there a way to adjust the Gauss elimination method so as to work here? So that, you know, of course, for 2 by 2 is not a problem, but the moment I give you a 3 by 3, the moment we pass to dimension 3, the operations will be much more significant, and you won't be able to find the inverse of the matrix in such a simple way. So this is where you might want to use the elimination method. So the question is this: is there any way that we can actually package both the steps of finding the inverse and then multiply v to the negative 1 times u in one step? And the answer is yes. Okay, and this is something really neat that I would like you to see. So here's how you do it. You do it as follows. You put the matrix V on the left, the matrix U on the right. So V on the left, U on the right, and then what you're going to do is apply the Gauss elimination method so that on the left, you get the identity matrix. Whatever shows up on the right is the transition matrix. Let me do it for you. So I eliminate the 2 first. So I have minus 2 rho 1 plus rho 2. And that would give me 1, 0, 1, 1, 0, 1, negative 1, negative 3, right? And then I'm done, right? I mean, I was lucky enough to have a 0 under the bottom one. So here's your transition matrix. So this was the easiest thing in the world, right? Which is, of course, the same as we found in the previous solution. Okay, and this is the method that I really want you to use. So I want you to juxtapose the matrix of the coordinates of the bases you're transitioning to on the left, of the bases you're transitioning from on the right, and then you apply your elimination. Okay. Of course, it will apply to 3 by 3 matrices. And this is why I showed you this, because I really think that for 2 by 2 matrices, you can do it either way, and the operations are fine. But now I would like to do a 3 by 3 example. And this is where I think that what we just did is going to be so much more, so much shorter. Okay, so let's do such an example. Okay, so find the transition matrix Yeah, so what you put on the left is the matrix of the coordinates of the vectors of the bases 2, meaning the bases you're transitioning to. And on the right, you put the vectors of the bases you're transitioning from. Okay? So in our notation, pretty much you put V on the left and U on the right, like this, pretty much. Okay? So find the transition matrix from the bases 1, to -1. One, 0, 1. Do we do what? I'm sorry, I didn't catch this. Here is certainly reduced row echelon form that you need to apply. Okay. 0, 1, 0 to the basis. One, 0, 0. One, 2, 0. And 1, 1, 1. Okay, so please go ahead and try to do this now by using the Gauss elimination method on this matrix right here. Okay, please give it a try for a few minutes and then we'll do it together. Okay, let's try together now. So first of all, what do we do? Let's write down the matrices so that you can just see them. So let's call this basis U and this basis V, okay? Or let me put it a little more. So let's say that this is the basis U and this is the basis V. Okay, what is a basis? A bunch of vectors that are linearly independent and generate the space. So every vector can be expressed uniquely as a linear combination of those vectors. So U is going to be the matrix 1, 2, negative 1, 1, 0, 1, 0, 1, 0, and V is going to be the matrix 1, 0, 0, 1, 2, 0, 1, 1, 1. So what do you want to form here? You want to put 1, 0, 0, 1, 2, 0, 1, 1, 1, and then 1, 1, 0, 2, 0, 1, negative 1, 1, 0. Okay. So the first one is already formed. The second one, all we need to do is make that pivotal. So I do 1/2 row 2, and that will give me 1, 1, 1, 1, 1, 0, 0, 1, 1/2. Yeah, V goes on the left, U goes on the right. That's the idea here. And 1, 0, 1/2, 0, 0, 1, negative 1, 1, 0. And then I need to eliminate 1 and 1/2 from the third column. So I will do minus row 3 plus row 1 and minus 1/2 row 3 plus row 2. Okay, and this will give me what? 1, or the last row is the one that remains the same, right? Because that's the one we're adding multiples of. The first row will be what? So you will get 1, 1, and then you will get a 0 right here. And then you will get a 2 right here. And then you will get a 0 right here, and then a 0 right here. And how about the second row? You will get a 0 here and 1 here, a 0 here. And then negative 1 times negative 1/2 is 1/2 plus 1, that's 3/2. And negative 1/2 times 1 is negative 1/2 plus 0, that's negative 1/2. And this again 1/2. And finally, you want to eliminate the 1 from the second column, the top one. So you will do minus row 2 plus row 1. So this will give you what? 1, 0, 0. 2 minus 3/2, which is 1/2. And then 1/2 again here, and then negative 1/2 here. And then you will have 0, 1, 0, 3/2, negative 1/2, 1/2, 0, 0, 1, negative 1, 1, 0. And that's it. That's it. So what is your final answer here? It's this matrix. So you can write that the transition matrix. So now you have a very formulaic process that almost disconnects you from what the real thing is that is going on here, which is much more evident if you consider the expression v to the negative 1 times u. But sometimes that's exactly what happens. We find a way to do something, then we package it in the most convenient possible way, and that's the way that we remember it. It's not ideal, but it's something that is very appropriate in such cases. Questions, please. As we said before, this matrix allows you to transform coordinates with respect to the first basis u to coordinates with second basis v. And that's why exactly I gave you the previous problem before that shows you exactly how this is happening. We already said that at the beginning. We said that one of our goals here will be to find a basis with respect to which a linear map is as simple as possible. If you're given the linear map with respect to one basis, and you find another basis for which the linear map is much simpler, then the transition matrix will allow you to find the new matrix of the linear map. And I'm going to discuss this in a little more detail in the next hour. Okay, so the transition matrix is going to enable you to re-express the matrix that you had with respect to the new coordinates. That's what it's going to do. Okay, and that's going to be the object of the discussion in the next hour. Are there any more questions before we take our break, please? Okay, then, why don't we take our break, and then we will be back with more. Okay, so welcome back, everyone. And let me see if we have any questions before we get to the second part that will really address the question of why we have been introducing transition matrices. And you're going to see that pretty much this could be considered as maybe the most, one of the most important constructions that we ever see in this course. Okay, then, so here's how it goes. So imagine that you have a linear map. And normally, like we said, in most cases, a linear map is going to be given to you with respect to the standard basis. But to make our discussion a little more interesting, let's suppose that this is given for the for some other basis. So let's say that T has matrix M with respect to the basis U. Okay, so suppose that this is the case. Okay, so in other words, according to the notation that we had introduced before, M is the matrix of T with respect to the base U on both sides of the computation. Okay, and now let's say that you have another basis V with respect to which you hope that M will have, that T will have a more convenient matrix to work with. So suppose that T is V is another basis. And that P is the transition matrix from the basis U to the basis V. What is the matrix of T with respect to the basis V? That's what we're asking. Okay. And the way to think about it is that you need to transition from the basis V back to the basis U, then apply the matrix M, and then reapply transition from basis U to basis V. So the way this goes is, so the answer is going to be the following. The matrix M that you had in the beginning works with U and U. So you input coordinates with respect to the basis U, and the output has coordinates with respect to the basis also U. Okay, so now, if you want to work with coordinates with respect to the basis V, what you need to do is change from V to U. How do you change from V to U? To change from U to V, you have the transition matrix P. So to change from V to U, you have P to the negative 1. And so this changes, changes from V to U. The matrix M computes T with respect to U. And then you need one more matrix, which will be now P, which changes from U to V. So that's the answer. So if you had to, if you knew the matrix with respect to the basis U, then that's how you find the matrix with respect to the basis V, and the main ingredient is the transition matrix. In fact, such matrices, so the matrices M and P, M, P to the negative 1 are called similar. So in the literature, you might find more often that the inverse matrix is on the left and the regular matrix is on the right. In that case, I would just have to have said that I need the transition from P. I would have had P to be the transition, not from U to V, but rather from V to U. But it's pretty much just semantics here. So most often we say, so we forget about transition matrices and we say that A and B are similar if there exists an invertible matrix U. I might want to use a different letter, so invertible matrix C, such that B is C to the negative 1 AC. So if you have a matrix and you multiply it on the left by a matrix and on the right by its inverse, or vice versa, it's the same thing, then you get a matrix which is similar to it. For all intents and purposes, similar matrices should be thought of as indistinguishable. Okay, so that's one of the main philosophies of linear algebra. So for all intents and purposes, similar matrices should be thought of as indistinguishable. Why? What's the philosophy that leads us to make such a bold statement? To say, you know what, if I have two matrices and they happen to be similar, meaning you multiply one matrix on the left by an invertible matrix and on the right by the inverse of that matrix, and you get your other matrix, then the two matrices, as far as we're concerned, are pretty much the same. What makes us say something like that? And the answer is that they pretty much represent the same linear map with respect to different bases. The idea is that they represent the same linear map with respect to different bases. That's why one of the fundamental problems in linear algebra is the following. So this gives rise to the following problem. Given a matrix M, find a matrix similar to M. Again, similar, don't try to interpret it in any concrete way that has to do with your understanding of the word similar, meaning that it looks like it. Similar in our case means that we multiply our matrix on the left by an invertible matrix, on the right by its inverse, or vice versa if you like, and that matrix is similar to the original one. So find a matrix similar to M, which is as simple as possible. As nice looking as possible. What do I mean by as nice looking as possible? What are the nice matrices that we have encountered that usually you would wish that you always worked with such matrices? What are the simplest matrices that we, okay, the identity matrix is the simplest one, but the identity matrix can only be assigned to the identity map. So I mean, it's a little too much to ask that, we're going to be working with the identity map. Instead, a more, modest requirement would be for the matrix to be what? What are the especially diagonal, right? Diagonal. So here I will put exactly. So what you just said has a name in mathematics, actually. We call them canonical forms. Okay, unfortunately, that part of the theory is considered too theoretical for this course, so we're not going to go there. But in some sense, you hit the nail on the head, meaning there are matrices that can represent everything else and are considered to be the simplest possible. Here are the bad news. They're not necessarily diagonal. So not every matrix is similar to a diagonal matrix. So let's put this. So not every matrix is similar to a diagonal matrix. These are the bad news. It would be so nice if every matrix was similar to a diagonal matrix. That's not true. The simplest example I can give you is this one. This is the simplest example of the matrix which is not similar to a diagonal matrix. Okay, so then you start relaxing the conditions and you ask, okay, so what is the next best thing after a diagonal matrix? And the answer is a triangular matrix, upper triangular or lower triangular, that sometimes does not matter, but you can ask, how often can I represent, can I have a matrix similar to an upper triangular matrix or a lower triangular matrix? And again, this is where the theory takes us to rather interesting places. And how interesting. This becomes rather, we go into much deeper aspects of the theory, and we're going to explore some part of it together. Okay, again, we're not going to look at canonical forms in any shape or form, but we're going to explore the fundamental question of when a matrix is similar to a diagonal matrix. We're going to get some partial answers to that, and we're going to even have a very nice word for the case that a matrix is similar to a diagonal matrix. We're going to call it, ready? Diagonalizable. Diagonalizable. So a matrix is called diagonalizable. I'm not sure this word will pass a spell check. Okay, there are many mathematical terms that simply do not pass a spell check. So a matrix is called diagonalizable if it is similar to a diagonal matrix. As we're going to find out, many interesting matrices in several instances are indeed diagonalizable. So, so A is diagonalizable if there exists matrix P, so that P to the negative 1 AP is diagonal. And therein lies the essence of the last problem from the homework for Wednesday. Look at the homework for Wednesday. Okay, it gives you this matrix A, right? And it asks you to compute it asks you to take B to be B to the negative 1 AP, and it asks you to compute B to the 10th. So first of all, you need to find P to the negative 1 AP. You need to find this matrix, right? So you will need to find the inverse of P, and you will see that it's an annoying matrix. If somebody asks you to compute the 10th power, and I am asking you in this particular problem to compute the 10th power, I could have asked you to compute the 100th power. And you would normally think that I'm out of my mind here. Okay, but the idea is that if you don't rush to say, okay, what is B? And then once you find B to do your computation, if you don't rush to do it this way, then there's something really good for you here. Why? Because you can do it the following way. You can ask, what is B to the 10th power? And try to write it out. Do you see what is going on here? These two matrices are inverses of each other, right? So this is the identity. And this will happen pretty much at all places. So all of these matrices are going to pretty much cancel. And the things that are going to stay behind are these A's. And how many of them are there? 10 of them. So this means that this will give you p to the negative 1, a to the 10th times p. And what is a to the 10th power? Well, a, if you look at what a is, you will realize that a is diagonal. Right? So a to the 10th is going to be simply b, 2 to the 10th is 1024, right? And 3 to the 10th is what? 3 to the 7th is 729. 729 times 27 is how much? Oh boy. Is 19,683. So you're going to get this. And then all you need to do is multiply on the left by p to the negative 1, on the right by p, and you're all set. Okay. There are other shortcuts, but the idea here, what I want you to understand is that if somebody asks you to compute a high power of a matrix, then you can do it very easily if you can actually diagonalize the matrix. And of course, again, somebody's going to ask here, and why do I want to compute a big power of a matrix? Oh, let's see, because here we have very simple reason. When you do a computation with a linear map, you pretty much do a computation with a linear map to see how things are transformed in a given space by applying the linear map. And then somebody might ask, what happens if you keep applying the linear map over and over and over and over? One of the instances where we have interesting situations like that is what is known as chaos theory, for example, where you keep applying the same transformation over and over and over to see what happens. And basically what we're saying is that if the matrix happens to be diagonal, then you have much better control over it than if it's not diagonal. So in other words, all of a sudden you realize that, we've been talking about linear maps and so on. Linear maps are maps that can approximate any map that you have, meaning something that gives you a transformation in any science, right? And then if you can diagonalize this map, you have a very easy way of understanding what is going to happen in the long run as you keep applying the linear map, or by approximation, what will happen as you keep applying your initial map. Okay, so in other words, the natural course of things that we have here is you look at general maps, you then approximate them by linear maps, you try to understand those linear maps as much as possible, and you hope that by that you are able to also understand your initial map, your initial function, the initial way that things transform. Okay, so you may think that the question that we're trying to answer here, which is given a matrix, what is the simplest matrix similar to it that we can possibly find? So think of it as one of the fundamental questions here.
Get off my screen.
And let me mute some people here. Okay. So if we think of this as one of the fundamental questions, then it simply turns out that some of the things that we're going to do from this point forward are going to be fully justified, because this is one of the main things that, one of the main questions that motivates the development of our theory from this point forward. Okay, and you will see this starting right away next time. Questions, please. Okay, let me take your attendance by asking you the following question. What number should I put here so that the determinant turns out to be 1? Okay, so try to answer this and give it to me on the as your attendance question for the for today's attendance. So what number should we put there so that we're actually getting determinant equal to 1? Okay, very correct. The answer is 3. Does anybody have any questions, please? I remind you that my office hours will be 20 minutes from now, and obviously we're going to have a quiz. We're going to resume our quizzes on Wednesday. We didn't have a quiz today because we had already had a quiz on the last material that we did on Wednesday before the exam. So don't worry, we will have quizzes for everything that we do. What is going to be the quiz like on Wednesday? Obviously, I'm going to ask you to find the transition matrix of between two given bases. That will be the quiz on Wednesday. Okay. Any more questions? Okay then. There's no homework due tonight, no, but there's a homework due on Wednesday. And we will have 6 more assignments, including this one, before we complete the 15 assignments that I promised you we would have this semester. Okay. I hope you're all doing well. I would like to speak to some of you who should have done better in this past exam. So hopefully we're going to have a discussion on this. And I will see you on Wednesday. Be well.